Humans start to learn language from birth, or even before. There is evidence that babies pick up the cadences of their mother's speech while still in the womb. The first year is spent sorting through the thousands of sounds human beings are capable of producing.
Babies can hear at birth every sound used by any natural language. So we now know they have them all there at birth. So the real question is, when do they lose or start to lose the ability to hear sounds that are not in their native language? It's around 10 months of age. Right around 10 months of age, English children start to lose the ability to hear sounds from Hindi and Thai that we don't have. Japanese children start to lose the difficulties with the ra-la contrast. And what's interesting about that is that's exactly when they start to tune in so well to the sounds of their language that they start to comprehend words.
By age 5, they're good at language. Well, they're good at certain parts, but there are a lot of things they still aren't able to master. And we know from a number of experiments that it takes quite a long time for them to get the details. The basic structure's there early, but the details take a long time to fill in. There's certain things about language that are probably not learned until 15 or 16 even. And I think there's a gross underestimate in the amount of time it takes to really master language.
That we learn language at all seems even more amazing considering what must happen for us to derive meaning from the spoken word.
Disengaged when it comes to the...
There's a lot that goes on. You have to hear my voice, my intonation. You have to put together the sounds. You have to figure out what sounds they are, what words those are. You have to go one step further and say, well, what is the sort of scene that I'm talking about if I'm talking about a scene? Put those all together in one thing that happens very quickly and naturally, and yet we know that the brain handles parts of those things separately and puts them together so quickly that you and I wouldn't notice.
Like most babies, when Paul Saylor learned language, the words were stored in the left temporal lobe of his brain, the same part of his brain in which his tumor later developed, a location known as a naming center.
The basic naming center down in the base of the temporal lobe can vary up to maybe 2 centimeters in each direction across individuals, but these category-specific regions of the brain can vary quite a bit more than that. And so we don't know from one person to the next exactly where those centers are likely to be.
To leave as much as possible of Paul's naming center intact, the medical team first created a map of that area. That meant that Paul needed to be awake during his surgery.
We first put the patient to sleep and we field block the patient's skull, so we give anesthetic to all the nerves surrounding the skull so that the entire scalp is blocked and no pain is felt during the latter parts of the procedure. After the brain's fully exposed, we can then start the brain mapping procedure, whereby we wake up the patient.
You may have heard that the brain itself has no pain or touch receptors, so it's not painful for the patient to be awake during the surgery. Now what happens is the surgeon brings out a separate probe that's hooked up to this electricity device, and the probe rests gently on the surface of the brain. And the patient is awake, and I start doing some language tasks with the patient. I usually will show them objects, so the patient will be talking and saying, that's a picture of a house, that's a picture of a bed, that's a picture of a tree. And while he's talking, at some point, I'll give the okay, and they'll press a button which puts a bit of electricity, a very small voltage of electricity, through that probe directly onto the surface of the brain. Now, if we happen to be directly on top of a language center, then during the period of time the electricity is on, the ongoing language process will stop. He will be talking tree, that's a house, that's a bed, that's a, what is it? It's a tree. And so what happens is they are interrupted in the process of grabbing those labels of those nouns. And they can't talk just for that period of time.
If the patient, if Paul in this case, can speak through the stimulation, then we know that area is a safe area to take out. If, on the other hand, he has a problem with speech, then we know that it's a more sensitive area and a more critically functional area, and that it's not safe to take out.
And then what we do is we move that probe all the way around the brain, millimeter by millimeter really, and map out wherever we think the language areas are, what the extent of them is, and we can see where the tumor is with respect to those language areas.
The surgical process, from my perspective, was kind of surreal, to say the least. And remember hearing sounds in my head that as I would term, were kind of a slurping, kind of a sound that I was later found out that it was, I didn't know at the time, but that's when he was actually removing the brain.
The map the medical team created during the surgery applies only to Paul. While our brains are all structured similarly, each individual brain maps the detail in its own unique way.
The way we learn is we literally, physically sculpt and change the brain. That's where we're doing it as adults. It's what learning is. It's a physical change in the brain. So the idea that language changes the brain, well, of course it does. Everything that is learned changes the brain. The infant brain is different from the adult brain because the infant hasn't learned language yet. When the infant has learned language, the brain will be reorganized, sculpted, committed. Parts of the brain now will have taken over the language job. And that's why a baby who has a left hemisphere stroke can acquire perfectly normal language. An adult who has had a left hemisphere stroke may have a very severe form of aphasia that's very hard to remediate, because after 30, 40, 50 years of handling the language task one particular way, the brain has adjusted and sculpted and changed, and it's very hard to go back.
I remember waking up and looking over and seeing my wife and seeing my mom and my dad, and I believe my brothers as well, and seeing them all and just knowing who they were and how I knew them, but I couldn't tell you their names at all.
Right after the surgery, Paul had a variety of language problems which were rather unusual and quite specific. He was able to speak fluently, so he's able to communicate and get along quite well. He could understand anything that anybody said to him. But when I did his post-operative testing, so what I would do is show him a bunch of pictures of objects, he couldn't name them.
I called his house frequently to see how he was, and his wife would relay information to me, and I would say, okay, just tell him that Dee said hello and that I hope he's feeling better. She said, Dee, it doesn't work that way. He doesn't know you as Dee. He only knows you as Diane, the supervisor.
The problem was extremely specific to two categories of items: animals and plants, or vegetables, any growing or living things. He was able to name the parts of living things, so he could name an arm, a claw, a beak, a wing without problems, but he couldn't name the animal that went with it.
Scorpion.
There you go.
He has a lot of trouble naming fruits and vegetables and animals, as well as finding names for people. It's very exciting to go to the produce market with him.
One of the ironies of Paul's naming deficit is that he is a volunteer for the National Park Service, where he talks to people about the importance of protecting living things.
And interestingly, it's not that the word areas themselves were damaged in the surgery, but rather the pathways that link those centers to the centers which allow him to find the sounds that go with them. It was those pathways that were disrupted.
The barn swallow captured a plump worm.
He also had a problem in reading. He was had a difficult time deriving meaning from the words that he would see.
When you read a word, right, it's visually processed. It comes in through the back of the brain, through the occipital lobe. It moves then forward towards language centers, where it is interpreted in different ways. A spoken word, in some sense, is a direct channel into language. A written language is a much newer thing, that our brain we can trick it and teach it, and we spend a lot of time learning how to read, but it's not something we would do naturally, except for a lot of schooling.
And it was determined to me that I had what was known as an acquired dyslexia, where I wouldn't be able to, I just slowly, it took me half an hour to read through a child's Winnie the Pooh book. And it was just a long, painful process.
Example 3rd, data transfer using markers.
And they've just now bought me a computer with a software program that does reading for me, where I can scan documents in, and it'll read those for me. I can get on the internet and read documents there. I can get emails, cut out stuff from emails, and it'll all read to me at different speeds.
Language is just one way in which human beings use symbols. In fact, all cognition, thinking, reasoning, decision-making, and problem-solving relies on our ability to symbolize.